we did this problem. True? You remember this one? And what was it specifically that helped us through this type of a problem? It was called unit analysis. So we analyze the units. And the way that we do that is with an equal sign, a long line, right? What goes to the right of the equal sign? The units that we're after, which in this case, it just says mass. So I don't know, we could go grams or kilograms. I'll just go kilograms. Then up here to the top left, what do we put? What they've given us, 2 quarts of mercury, 2.0 quarts. All right. And then I use a conversion factor. So I put in a fraction right here, right, that has units. What are on the bottom? Quarts. Quarts have to be on the bottom because I need to get rid of quarts there. And hopefully, something in your mind will know a conversion factor that contains quarts, or something in the problem will know a conversion factor that contains quarts. And we're going to keep doing this until we get to kilograms. So what? I don't know anything about quarts, right? We just know that it says there 1 liter is equal to 1.0576567 quarts. So looks like I can go to liters, right? And I think sometimes it's better to set up your units before you worry about the values themselves. So what goes down here then? Liters. And what am I going to do to go to liters? We use liters. Okay, milliliters. Now, that might not be very intuitive. You might not have any other ideas. I mean, you might say, maybe I want to go to megaliters, or I don't know. It is helpful here that we can see that they've given us some information about milliliters there. So that might be a little bit of a hint to know to go to milliliters. Units down here now. Milliliters. Up here, well, if I can get towards kilograms, and we see that they have given me the density, which is in grams per milliliter, so that helps. Okay? And then grams has to go down here, and I know a relationship between kilograms and grams. Now I just have to make sure I get the right values in here. What's this one here? 13.69 grams per milliliter. Okay, did I do it right? Yeah. All right, that one's wrong, huh? Okay, good. Now, if we were given this, hopefully everybody knows how to calculate the right answer in a calculator. Is that true? Anybody want to go over how I would calculate the value, the answer at this point? I think I've told you, it's your duty to tell me if you're lost, if you don't know what's going on, okay? You have to raise your hand and say, okay, I must have missed something. Hey, can you help me figure out what's going on? All right, so apparently we're hearing that everybody knows how to calculate the answer given this information. All right, excellent. So here's another one that I would like to, for you to try to answer right now. If I have 2,163 grams of ethanol, how many milliliters of ethanol is that? Okay, the density of ethanol is 0.755 grams per milliliter. All right, so talk to your neighbors. Use the method. Again, we only got 2 numbers, so it's like this times this, that divided by that, right? But instead of trying to rely on that sort of intuition or experience that might or might not be there, use unit analysis to know exactly what needs to happen here. Do you want to spread? Mind if I open up this window here? There we go. Praise the day. So here's the one we're focusing on right now? Yep, 2,163 grams of ethanol. I'll be right back. Do we get it? So, hopefully everybody has what on their paper? Everybody should have this, and if you had any ideas here, the units should be there. What is that? Milliliters. Okay? Now that much is like 0 brain cells, right? So I think that we should all be able to have that. Now if you don't have that, what this is this is like a pathway. This is a map, a goal, a vision, right? If you don't put that down, then there's a disconnect. There's a lack of trust. You don't think that the method is helpful to you. You think, just tell me the numbers and I'll divide them, or whatever it is. But this is what you need to have down. Now, it might take a little bit more effort to decide what goes here. What goes here? 2,163 grams. I would say, though, the effort is still relatively low. Even the next step, almost no brain cells. What goes down here? Grams. So that to there, I would expect everybody to be able to set up. Now, the next thing you might be stuck on, right? But this should guide you. If there's a way, what would I like to have up here? Milliliters, all right? And then hopefully I can stare at this long enough and realize what this is, right? Because this is 0.755 grams for every 1 milliliter, which can also be stated as 1 milliliter is 0.755 grams, right? So 0.755 grams for 1 milliliter. And then that'll give us our answer, right? Okay, anybody want to talk more about this one? Yeah. No. Yeah.
So, on the exam, would you be able to, or would we have access to a chart where you can find different measurements where you can find like quarts and liters and stuff like that?
Yeah, all the conversion factors, that they're called, that you need to know are the ones that we talked heavily about, which are centimeters to meters, millimeters to meters, micrometers to meters, and nanometers to meters, right? And even micrometers and nanometers, they don't really put too many things on there. So if you rely heavily on centimeters and millimeters, you'll be fine. And then the other way, kilometers, and really that's about it for kilometers. But we talked about wanting to know megameters and gigameters, or giga, mega, and giga, those prefixes. So that's about all that you'll be needing to know at this point in terms of conversion factors. Okay. So let's see. All right, here's one that we should pay some attention to. Convert 124 feet squared into square meters. So, convert 124 feet squared into square meters. This one is even easier to set up because they just like flat out say what you're going to do, right? So everybody should be able to write the equal sign, draw the line, make the line big because we're not concerned about wasting paper. Give yourself plenty of space. We don't know exactly how many conversions it's going to take. This top one up here, can you read it? Exercise 7. What goes to the right? All right, like this, meters squared. What's the top left? 124 feet squared. Okay. So, do we know what goes down here? What goes down here? Feet squared. We know that because we need to get rid of those units, right? And we'd like meters squared. Does anybody know how many feet squared there are per meter squared by chance? Without looking on Google or anywhere? All right, that's not something we know. Anything else we might know? What we usually convert feet into to get to our metric system? Inches. All right. Anybody know how many inches squared there are in a foot squared? How many? 12? Well, maybe. It depends on your perspective or what you mean by 12. But this here, let's say I've drawn now 12 inches by 12 inches, or in other words, 1 foot by 1 foot. Right? So if that's 1 foot squared, how many inches squared is it? What's that? 144? Is that what you said? Yeah, 144 inches squared. True? Everybody can see that? So 1 foot squared is 144 inches squared. Another way that we could have done this is like this, where we say 1 and 12, but we have to square both of them. All right, that's another way we could have done that. So we're in inches squared now. So what's going to go down here? Inches squared, let's go to what? Centimeters squared. What's the number for inches to centimeters? 2.54 and 1 inch. And what did we say we're going to have to do with these? Square them both. Okay, now centimeters squared to meters squared. Did I skip too fast? We knew that centimeters squared had to be down here, right? And we want to end in meters. So what values go here? 100 squared and 1 squared. All right. So the only new wrinkle here is that we're dealing with squared, right? So our conversion factors like 1 to 12 or 1 to 2 and 2.54, we have to make sure that we square them if we're looking for square units. Okay? Anybody get an answer? How is our search for calculators coming? One girl was very upset in last class that she had to buy a calculator. She said, "This is my only science class. I shouldn't have to buy a calculator." And yeah, if you go through your science class without buying a calculator, then you'll get exactly what you invested in, right? The inability to build that relationship with that calculator and approach scientific matters, I don't know, the way you should approach them. So I would definitely invest the, online, $20, $15, a little bit of work, go to Amazon or what do you call it? eBay, right? eBay's where you get your used stuff. So just find one. And if all else fails, go to the bookstore and buy one for $120 or whatever, right? I mean, comparative to what you're going to be learning for that amount of money, it's a steal, right? It is a steal of a deal. Okay, did anybody get a value here? Is it a hard one? Did you guys get a value? 11.5 meters squared? That's probably about right. Anybody else get that? Why aren't we getting any? Nobody has a calculator? Is that the problem? You have a nice calculator. Oh, you got 11.5? Okay, great. And did you get 11.5 too? Perfect. All right, then. You know what this means? This means we're done with chapter 2. Wonderful. Are we behind or are we ahead? Does anybody have the syllabus by them? By chance? I feel like we're a little ahead, but we might be right on time. Here, chapter 3 notes. Oops. Did you guys get that last one? No. That's the problem. Are you guys getting along? Okay. Maybe I got to come back here and make sure you guys are doing okay. Where are we at? Right on time. All right. Good. Today is supposed to be chapter 3. Sorry, I gave it. There you go. Okay, then. The first part of this chapter starts talking a little bit about how atoms were formed, introduction to atoms. What happened to our slides? Or did I? Did I turn that off? Oh, there we go. That's interesting. Okay, so here we are. So there were some kind of major experiments that contributed to our understanding and what we now have as our model of the atom. And we'll introduce some of these things. I wouldn't get too hung up on trying to memorize this stuff. Just absorb it like it's a good movie or something, right? Rarely will you have problems where they say, what was Rutherford's experiment like, blah, blah, blah. And if they do, you can miss those questions. That's not worth it. I don't know why they do that sort of thing, right? So you can just kind of absorb this and say, okay, all right. And you're not going to get it all, but we'll do our best. But one of the inventions that allowed people to learn a lot about the atom was electricity, and specifically using electricity in the absence of oxygen or any other thing for that matter. Because electricity is nice and you start performing a reaction on material. But the problem is oxygen, which is readily available, about 20% of the atmosphere, is pretty reactive. So it was like the reason why people couldn't discover stuff for a long time. Because they thought, this thing's gaining mass. Where's it coming from? Oh, it must be from the ether or from the gods or whatever, right? This thing's losing mass. Where is it going, right? So losing it as gas or gaining it as oxygen because oxygen's relatively reactive, right? So once we had the ability to create a vacuum, and a cathode ray tube is a vacuum. Whoops. What's going on here? Why is it doing that? Okay. Oh, okay. There we go. Were any of my slides up there before? All right. Oh my goodness. So many variables, always different. All right, so a cathode ray tube is a contained area, region with nothing in it, right? We pull a vacuum, we get everything out, but we allow two little metallic electrodes to enter, and then we apply a voltage there, all right? And what happens is when you apply a voltage, then you will produce the movement of electrons from one side to the other, right? And they didn't know what these electrons were initially, but they began to recognize that these electrons, when they would hit certain chemicals, would make those chemicals glow. So inside this cathode ray tube, they put a white piece of paper that has some phosphorus on it. So when the electrons hit it, it glows, right? I don't know if that green color looks familiar to you, but in the olden days, this is the only color that you had for computer monitors and televisions, right? This was it. And this is how the gentleman who invented the television decided, hey, we can transfer images based on the movement of this cathode ray. And so what they do next is they bring in a magnet and show how the cathode ray responds to a magnet. So let's bring in the magnet. There it is. And it would deflect the ray, and so you could control how much magnetic field you would place on the cathode and you would decide where it would position itself, right? So you had magnets all around this cathode ray. You would bend it up to the top corner of the screen and then bend it in different spots along the whole screen, little by little, right? And you would just have it do that every, 20 times a second. And you could choose whether you wanted on or off. And so you could choose if you wanted green or no green and where you wanted it. And it would just be doing that the whole time, and then that would be an image, right? So the movement of, or not the movement, but the movement of the ray, which was electrical impulses on the magnetic field, right? Magnetic field impulses, and whether or not the ray was on or off ended up being the information necessary to kind of record and send pictures from place to place. It also told them that this thing that was moving across, it didn't matter what element they used. Whatever element, whatever material they had in here, you would see that same beam. And because of its negative charge, they identified that all atoms had a negatively charged component to them. All right? There's this other experiment, which is kind of interesting, and I don't know why it found its way here. It's interesting, but not terribly interesting, but clever. This gentleman, Robert Millikan, produced a spray of really fine mist, like from a perfume bottle, really fine mist of oil. And he had two plates, and the top plate had a hole in it. So the mist would slowly have some droplets fall down to this plate and hit that plate. He would charge these plates, and the oil would still fall. But then when he introduced an X-ray beam that would drop electrons off onto the oil droplets, he would see the oil droplets stop falling and begin to rise because of the charge that was on the plates. All right? So, one more time. Spray. There we go. So he sprayed it, in came the oil, it would drip down like this, and as the drips came down nice and slow, he would introduce X-rays. Someone hit the drops, and then the charges on the plate would make the drops slow down, stop, or even start moving the other direction. And he could tell by the rate at which they would move and the amount of energy that he had applied, the voltages that he had applied, he calculated the charge on an electron, which was a big step, right? He could actually know how many electrons there were and what the charge on a single electron was. All right, another big experiment which helped us come up with, from the preliminary, not preliminary, but from the beginnings of the data that was being collected, they had this idea, that an atom was, they call it a plum pudding model, where they knew that there were some things that were positively charged, some things that were negatively charged, right? And it was all kind of moving together. And they knew that the number of positive charges was the same as the negative charges because it was equal, it was neutrally charged. They knew that they could remove an electron or not remove a proton, or add an electron, and then you could get a species that was either negatively or positively charged. All right? But this was kind of the model that they were working for. But they also had this feeling that relative to the whole size, most of it was empty space, because they would shoot X-rays, little tiny particles, at thin pieces of foil, and the particles would go right through. All right? So that's what this Rutherford's thin gold foil experiment showed. He would shoot tiny little atoms, actually helium atoms, at this gold plate, and most of them would go right through. But he noticed every once in a while one would scatter at different angles. And he looked at the angles at which they would scatter, and he did the math to try to calculate what kind of force must be there. And he came up with an idea that the atom must have a small, dense nucleus of positive charges, where the rest of the outside here is mostly empty space with negative charges. All right? So that got us closer to our model, and basically to our model that we now kind of share with the world. Talk about, this is generally our model that we use. And it's limited, doesn't answer a lot of things, but it's got us pretty far. So, later on, they discovered that there was more mass in the nucleus than just positively charged things. And what was the other stuff in the nucleus that didn't have a positive charge? Neutrons. Neutrons, right? And we talked about this like day one. You guys know generally the subatomic particles. Positively charged are our protons, neutrally charged are our neutrons, and electrons are negatively charged. Right? And one of the major things to remember here is that the mass difference between electrons and protons is relatively large. Right? It would take more than 1,000 electrons to get the mass of a proton or a neutron. It's also worth noting that protons and neutrons have pretty much the same mass. Okay? Okay, good. Now, when we write elements, we have these symbols, these letters, and we've already talked about these letters. And sometimes you'll see, when you just write the elemental symbol of something, sometimes you'll see numbers around it, like a number right here, which would be something like 24. And that is telling you that this atom, chromium, has 24 protons. 24 protons. Now this was kind of an old style because back then the periodic table wasn't as readily available just everywhere, right? And so this was a way to tell people that it had 24 protons. But if you have the periodic table up on the wall, chromium, we can always look up here and know how many protons it has by looking at that number. Right? Okay? How many protons then does neon have? 10, right? Any questions about that? We just find the element and we know how many protons it has. And if it's neutrally charged means that there's the same number of what? Neutrally charged, what does that mean? Same number of protons as what? Electrons? Is that okay? Is everybody comfortable with the word neutrally charged? I printed up some things for you guys, but I can't find them. Where'd they go? Printed up some nice periodic tables. It's okay, we'll get them next time. Or maybe if I have a chance, I'll go get them. So that number isn't always necessary, right? You also might see a number up here like that. All right? Now this number is not going to be on the periodic table. But what it is it's the number of things that are in the nucleus. And what kinds of things are in the nucleus? Kind of subatomic particles, protons and neutrons, right? So if this says 40, how many protons did we say chromium has? 24. So how many neutrons must there be? 40 minus 24? 16. See how we did that? So the number up top here is the total number of subatomic particles that contribute to the mass of this atom. So sometimes they'll say that's the mass number. All right? Notice that it doesn't matter how many electrons there are, it never contributes significantly enough to be included in the mass. Okay, good. On the periodic table, we have not mass numbers of elements, but average mass numbers of elements. So let's look at iron, for example. Iron, how many protons? 26. And then it has a mass number there of 55.847. Okay? Now that mass number isn't a whole number, right? So why isn't it a whole number? Anybody have any ideas? What contributes to the mass of the atom? Protons and neutrons. How many neutrons must there be if this is iron 55.847? How many neutrons? Figure out with your partner. How many neutrons must there be if that's iron 55.847? It's going to be a fraction, right? How many is it? $55.8 minus 26. What did we get? 29.47. What? Okay, 29.847. So there's 29.847 neutrons. And how many protons? 26 protons. All right? Why is there a fractional number of neutrons? Well, this isn't how many neutrons there are on every atom. This is the average number of neutrons on every atom. So that means sometimes you get iron that is 59, right? I'm sorry, 56. 56. And sometimes you get iron that's 55, maybe. So if I have iron 56 and iron 55, how do these differ from each other? Neutrons. They have a different number of neutrons. And we have a name for elements or atoms that have differing number of neutrons and the same number of protons. We call these isotopes. All right, isotopes. So that number up there is the mass of the atom on average. If you were to gather all the isotopes, that would be the average mass. Okay. So we have our atomic number here, and we have our mass number there, mass. All right, so if I said cobalt 60 and bromine 81, can you identify how many neutrons, protons, and electrons are on these species? See if you can fill that chart out with your neighbor. That's the third row there, and we're trying to fill in the symbol for that scenario, yeah. So what do you think? How many? What's the easiest one? The easiest one's probably the protons, right? Because you can just look on the periodic table and see it. Can you guys see okay from there? Okay. For what? Cobalt? Yeah, 27. Hey, while you guys are filling these out, I'm going to go get those periodic tables. Did you get it? There you go. There you go. Your very own periodic table. There you go. Okay. Did everybody understand how to fill that chart out? Did everybody get the role for today? Okay. There you go. All right, let's see how you did. How many protons in cobalt, first of all? 27. Cobalt 60. How many neutrons? Sorry, how many neutrons in cobalt 60? 33. And how many electrons then? 27. Oops, what happened there? Oh, hold on. Those values are correct. Okay, how about bromine 81? How many protons? All right, how about how many neutrons? 46. All right, electrons? 35. Very good. So, how do we know the number of electrons is the same as the number of protons? Because there's no charge on these species, right? It's just neutral. So what does this represent then here? What do we got? Copper, 65. Now the 65, what do we call that again? What's that number up at the top left? The mass number. Mass number. Very good. Excellent. So that puts us in a situation where we can answer these types of problems, well, theoretically, although these can be kind of difficult to kind of think about. But we need to be able to answer these questions because this is the type of thing that you would see on a quiz or a test. So what we have here is a mix of two different isotopes, two different isotopes, chlorine 35 and chlorine 37. All right? And chlorine 37. And that means these two differ from each other by the number of what? Well, they have the same number of protons. They're both chlorine, but they have different number of neutrons. Okay? Now, what would the average, so they give us the masses of chlorine 35 and 37. And 35, chlorine mass of 35 is 34.9689, and that of 37 is 36.9659. So these aren't exactly 35 and 36 because the masses that we're given are actually fractions of hydrogen, where hydrogen is kind of identified as a unit, one unit. So they're not exactly the same value, right? So the mass of this is 34.9689, and this one is 36.9659. If I had a bag of chlorine here, chlorine atoms, and half was 35 and half of it was 37, what would the average mass of an atom be when I pulled it out of the bucket? It would be these two added together, divided by what? Divided by 2. All right? That's how you would find the average of these two. But what if 75.77% of the atoms are chlorine 35 and 24.23% of the atoms are chlorine 37? Now can we find the average mass? Would it be just these two things added together divided by 2? It wouldn't be, right? So how do we fix that? How do we answer that problem?